So now we're going to look at question 5. And question 5a, we're asked to solve or find the complex solutions to this equation, z cubed equals minus 1 plus I. So we have to find the third roots of this complex number, minus 1 plus I. There's going to be 3 of them, of course. And the question also asks us to plot these solutions on an organogram diagram, so on a diagram of a complex plane. So in order, if we look at the solutions over here, in order to take the third roots, to find the third roots of this number, we should convert the number from Cartesian form into the polar form, or the exponential form, sometimes called, where you express the complex number as its modulus times e to the I theta times the exponential of I times theta, where theta is the polar angle. So for this complex number minus 1 plus I, its modulus is the square root of 2, and the polar angle is 3/4 of pi. So then the solution z will all satisfy this. They'll be able to be expressed as that complex number to the power of a third. And you notice here that we put in some multiples of 2 pi I. So this will, of course, increase the polar angle by 2 pi, or some multiple of 2 pi, but of course that won't change the complex number that we're referencing, because 2 pi is a complete turn, 2 pi radius around the origin. And if we put in various values of k here, we will get various that will move around between the three different roots. So if we take k equals 0, 1, and 2, we will get the 3 different roots. So you're taking the third power of this. So when k is 0, in all cases, the modulus of the solution z is going to be, we've got 2 to the power half here, and when you raise it to the power third, it'll then be 2 to the power sixth. So that's the modulus of the cube roots. And when k equals 0, so we don't have this extra angle term here, so taking the third root there, we'll just have e to the I 3 pi over 12. And when k equals 1, we'll have 11 pi over 12, and when k is equal to 2, we'll have 19 pi over 12. There's no need to take further values for this parameter k, because you'll end up just re-expressing these same 3 roots with a larger polar angle. So those are our 3 solutions there, expressed in polar form. There was no particular requirement to express them in Cartesian form. It wasn't asked for, so we won't do that here. And then these 3 roots will lie on the circle of radius equal to the modulus to the 6th power to the 6th root 2. And they'll be equally spaced around this circle, so the angle between each of them will be a third of 2 pi, or I've written it as 120 degrees here. So as I've used the computer to draw a plot of where these 3 roots z1, z0, z1, z2. But any kind of relatively accurate hand-drawn plot will be okay as well. Okay, so moving on to part B, you are asked to write down the Cayley table for the group Z15. Okay, so what this here is, this is the multiplicative group of congruence classes modulo 15. So the modular arithmetic group of integers modulo 15 under multiplication. We're asked to identify all its cyclic subgroups and then explain briefly how the statement of Lagrange's theorem is verified. So first of all, if you're going to do the Cayley table, we've got to say what the elements of the group Z15 are. So remember, the numbers that are in the multiplicative modular arithmetic group are all of those that are co-prime to the modulus. So we only include the integers between 1 and 15, which are co-prime to 15. So in other words, we want to not consider any multiple of 3 or 5, okay, because they will share a non-trivial factor with 15. So the remaining ones then are 1, 2, 4, 7, 8, 11, 13, 14. All the multiples of 3 have gone, and all the multiples of 5 have gone. So these are the elements in the group, and here is the Cayley table for the group, or the multiplication table for the group. Let's just look at one example. 4 times 7. So 4 times 7 in the normal sense, of course, is 28. But then you want to consider the congruence class of 28 modulo 15, and the output of the operation is the standard representative of 28 modulo 15. So 28 is equal to 15 plus 13. So 13 is the congruence class of 28 modulo 15. So that's why we see a 13 here in the entry 4 times 7. Of course, you also see in the same 13 in the entry for 7 times 4, because of course multiplication, even modular arithmetic multiplication, is commutative. So the body of this Cayley table here will be completely symmetric around the main diagonal. Okay, and now to looking at the cyclic subgroups. So the cyclic subgroups are the groups that are generated by a single element. Okay, well, 1 is the identity element in this group, so it only generates itself. Let's look at the cyclic subgroup generated by 2, for instance. So 2 to the power 0 is, of course, the identity 1. 2 to the power 1 is 2. 2 squared, okay, well, reading off the table, we can see that 2 squared is 4. 2 cubed is 2 times 4, which of course will be 8. What is 2 to the power of 4? Well, it's going to be 2 times 8. But if you look at the table here, 2 times 8 is equal to 1 in this group, so you're already back to the identity. There's no point in looking at any higher powers of 2, because they will just continue to cycle through these same 4 elements, 1, 2, 4, and 8. When you repeat that analysis, testing out all the other elements here for generating cyclic subgroups, these are the groups that you get. Now I've shown them here for the generators 1, 2, 4, 7, 8, 11, 14. The ones I've omitted here are 13. 13 is going to generate the same cyclic subgroup as 7 there. Okay. Now, how does this verify Lagrange's theorem? Well, Lagrange's theorem for groups, a finite group, says that the order of any subgroup, meaning the size of it, the number of elements in any subgroup, is a divisor or a factor of the order of the containing group. So what kind of sizes of subgroups are we seeing here? We're seeing subgroups of size 1, 2, and 4. The containing group, set 15, has size 8. So the way Lagrange's theorem is confirmed here is that the sizes of the subgroups 1, 2, and 4, those are all factors of